Welcome back to the Design by Analysis series. I am Pro, a professional engineer with experience in advanced pressure vessel and component design. So far in this series, we have covered protection against plastic collapse using elastic limit load and elastic plastic methods. And we also looked at protection against local failure using both elastic and elastic plastic criteria. Now we move into what is arguably the most important section in ASME design by analysis: protection against failure from cyclic loading and fatigue. This is critical because fatigue is one of the most common failure mode in pressure equipments, especially under repeated pressurization, thermal cycle, and mechanical loads. This section will be divided into three videos. In this video, we will start with fatigue screening. The next video will cover elastic fatigue analysis, and then we will move to the most detailed approach, elastic plastic fatigue analysis. Together, these three videos will give you a full picture of how ASME Div 2 addresses fatigue in part 5. Our fatigue example is PTB-3 example 5.5.2. We are tasked with evaluating the fatigue screening of a nozzle to shell junction using method B as per clause 5.5.3.4 in the 2025 edition of ASME Section VIII Div 2. The goal is to determine whether this component passes the screening criteria, in which case a full fatigue analysis can be waived, or if not, then a detailed fatigue analysis will be required. The model reused from example 5.2.1, which already studied earlier for plastic collapse. The nozzle material is SA516, shell and head material is SA105, design pressure is 380 psi, cyclic life requirement is 20,000 full pressure cycles, and startup and shutdown of 20 cycles. So the fatigue check will be based on a total of 20,000 20 cycles. Clause 5.5.3 defines the screening criteria for fatigue analysis. This section allows designer to determine whether a fatigue analysis is even required for a particular component. If component passes any of the screening checks, a detailed fatigue analysis may be skipped. There are three methods in 5.5.3. First is method A, method B, and method C. So method A is only be used for steel component with specific minimum tensile strength of 80 less than 80 ksi and a different loading condition as well. Method B is most used. This procedure may be used for all materials with a designated smooth bar fatigue curve mentioned in Annex 3F1. Method C is mainly for welds. Clause 5.5.3.4 fatigue screening method B. So let's talk more about this method. This method is not limited to steels like method A. It is applicable to any material that has a fatigue curve, or we call it SN curve, listed in Annex 3F1. There are a couple of steps that we follow in this method, which makes it very easy uh, to complete the process. The step one is define all cyclic loads like startup, shutdown, etc., which we have already done in the previous slide. Then the most important part in this one is to get Kfb and HC from weld quality and geometry. So Kfb depends upon the weld quality and HC depends upon the geometry. So these are the factors we need to get for this method, and we can refer table 510, 512, and 513 of ASME section 8 div 2 to get these values. We'll come to it in the later slides, how to find the value of Kfb and HC. The next step is to find all the loading conditions, so pressure cycles, fluctuation, and also get all the loading condition. And then the last step is to find the damage. So in this case, let's say that df is a total damage, and it's the addition of all these damage from every loading condition. So let's say in this case dfp is full pressure cycles dfp, so damage done by this cycle plus the damage done by the remaining cycles, this should be less than 1. So in this case, if you don't have other loading cycles, you can ignore them, and let's say you can consider only one pressure cycle, and the damage from that cycle should be less than 1. If that criteria is met, we don't have to do this method, fatigue analysis. The materials are same. We are using example from 5.2.1 previously, so I'm keeping the same example as in PTB-3, so that with the same example with the same loading condition, we can understand more about how this ASME guideline can be applied. So first, fatigue strength reduction factor. So as we saw in the previous slide, there are two factors. One is Kfb and one is SC. They are called as fatigue screening criteria factors for method B and C. We can refer table 510 to 513 for to get the values. So in this case, KFB, since our part is an integral welded joint, it's a fillet or non-flushed weld. So in that case, the value is 3.0. There are many different values as well. If it is an integral weld, if it is non-integral weld, and so on. So you can decide the part or the location for your part, and you can get the criteria from there. SC is for nozzle. This is for geometry. So in this case, nozzle is not in the knuckle region, so the value is 1.0, and there are many other values as well based on the geometry. So you can choose those. So in our case, the KFB is going to be 3.0 and SC is going to be 1.0. They comes from table 510, 512, and 530. I'll show you in the next slide what is the use of these factors and how we're going to use these factors in our approach. One point to note is that this differs from what is provided in PTB-3. As example in PTB-3 is based on earlier edition of ASME Code. In that version, the fatigue screening method was different and relied on factors such as C1 and C2. However, in the 2025 edition of ASME Section VIII Div 2, the fatigue screening formulas have been revised and updated. Factors such as Kfb and HC are now used. So I wanted to have this as updated as possible. So the criteria is right here. First, we need to find how many total number of cycles our part is going to face. So required full range pressure cycles including startup and shutdown is 20,000 plus 20. That's 20,020 cycles. So the number of allowable stress for a pressure range is KFB HC3S by 2. So this is the stress actually. So this is the stress. At this stress, we need to find the life a part can handle, and then we get a damage uh, with respect to this stress, and then we compared with the number of cycles our part is going to face. So the value of kf hc we have got in the previous slide from table 510 to 13, and 3s is the allowable stress. So in our case the value is I think 23 point something for s, and if we multiply these values here we get the stress of 110. So what does this n 110 mean? This means we need to find the life for a part for which the alternating stress is 110 ksi, and so which is shown here, and the damage in this case is the number of cycles, the number of required cycles for the test, and the number of cycles by the criteria. So if this damage is less than 1, then the fatigue analysis is waived. We don't have to do the fatigue analysis. Why? Because these criteria are very conservative. So if we meet this criteria, we don't have to do the fatigue analysis. But if this criteria is not met, if this value, the value of damage is greater than 1, we have to do the screening method, and we have to do maybe a elastic fatigue analysis or maybe a elastic plastic fatigue analysis. We'll go on to those in the next videos, but for this one, let's check if the fatigue criteria is met for present case X3F. So I have laid on a couple of steps here that we need to follow to get the life using NX3F. This is pretty straightforward method, but we need to know a couple of things before we start the process. The first thing we need to know is the alternating stress on which we need to find the life. In the previous slide, we find that alternating stress is 110 ksi. For that, we need to find how many lives the part is going to sustain for this stress. So using 3F1 smooth bar design fatigue curves, alternating stress is 110 ksi. The next step is to find the value of y. Y is the stress amplitude temperature correction factor. How do we find the y? To find the y, there is formula is right here. First, we need to find cs. The cs is a unit conversion factor. For ksi, it stays 1. You can get these values for other, if you have the units are different, you can get the value of cs. It's given in the annex 3f. In our case, since the values are ksi, so we're going to use cs as 1. So the formula to find y is log sa by cs. So in our case, sa is 110 and cs is 1, so y is going to be 2. So you get a value of y. The next is section in that is 3f1.2a1. So we need to know the type of the material that we have. So in our case, the material is carbon steel, low alloy steel, which is a series 4xx stainless steel. There could be 3xx stainless steel depending upon the type of material. So in our case, we're going to use 4xx steel. And then there are two different formulas. Either you're going to use the first one, which says if the UTS limit is less than 80 ksi. Our UTS is 70 ksi, so we're gonna use the first of the formula. And now the next step is to find again, to use, there are two equation in that section, equation 3f3 in that section. The first one is that we need to find the value of 10 raised to power y. So if the value is 10 raised to power y is greater than 20, we're going to use the formula which is given here. If this value is less than 20, we're going to use a different formula. So in our case, let's find out what is the value of 10 raised to power y. So 10 raised to power y, we get the value of 110. So since 110 is greater than 20, we're going to use this formula to get the value of x. So once you put all these values in that, we only need to put the value of y, as you can see right here. So once we put the values of y, we get the value of x. And now I'm going to show in the next slide what is the use of this x and how we get a life using this x. Now the next step is to find the life. We are again using again annex 3f. So the criteria which says the life at this value, so uh, kf multiplied by sc multiplied by 3s divided by 2. So this we found in two slides back. This value becomes 110 ksi. So this is the alternating stress. So we need to find a life at 110 ksi alternating stress, and the life of this is 10x. This comes from annex 3f. We just now find the value of x, which is 2.6.48. So when you put here and you get the life, you get 444 cycles. What does this mean? This means that at alternating stress of 110 ksi, at alternating stress of 110 ksi, the part is going to have a life of 444 cycles. And this is a very conservative method, and that's why this comes from the fatigue screening factor. So the criteria here is the damage. We need to find the damage. So this number of cycles that we had, the part must go is 20,020 cycles. But from the criteria, how many cycles the part can last is 444 cycles. So obviously this damage is greater than 1. So if the damage is greater than 1, the criteria is not satisfied and a detailed fatigue analysis is required. So now we have to stop here, and now we need to move to fatigue analysis. This is an excellent example of why screening is only an initial step. It is a quick way to eliminate cases where fatigue analysis is clearly not an issue. But for components like this, we must go deeper. In the next videos, we will do exactly that. We will perform both an elastic fatigue analysis and an elastic plastic fatigue analysis using PTB-3 example. Always remember that this video is only for educational purpose only. For actual design and compliance, you must use the official ASME boiler and pressure vessel code and PTB-3 guidance. If you find this useful, don't forget to like, share and subscribe so you don't miss the upcoming videos. These are the most important parts of DBA, and they will give you a full understanding of how to apply ASME rules to real world pressure vessel design condition. Thank you.